Okay, so I'll go through a little bit of just set theory with some political science examples to give you a sense of why the stuff covered in the readings is important to us. So first we begin by defining a set, and a set is a bounded collection of objects or elements. It is denoted with curly braces, so when you see those curly braces and people are talking about set theory, you'll know that that means the set. So for an example, the set of all positive even integers less than 10 is 2, 4, 6, and 8, right? And so I just use the curly braces to define that set of numbers. Alternatively, I could use this notation where I have the curly braces which read the set, and this notation here reads the set that contains all values labeled x, so all values labeled x. You see these colon, that means such as, or such that, x, right here, x, is greater than or equal to 0, right, greater than or equal to 0, less than or equal to 10, and, right, the comma means and, x is part of the real number line, right? So this you read as part of, and this you read as the real number line. If you don't know what the real number line is, you should go look that up on Google now. And so why would I write this out like this, right? So this is a little more confusing than just writing this, right? It's a little more notation. Well, you would use this type of notation if the set you were talking about was very complex. So if the set contained hundreds and hundreds of values or hundreds and hundreds of elements and events, then you might want to use this notation to summarize it up succinctly for your reader instead of something like this. So this is, you wouldn't need to write this notation for this for values, but for something more complex that would be helpful. Right, so it's useful for large sets with many elements. So then we need to define set outcomes, and the first definition we want to define is what is a sample space. So we refer to all the potential outcomes, right, and the key word there is potential outcomes, within a set as sample space, right? And so if we take a coin flip, for instance, the sample space of a coin flip is either heads or tails, right? So those are the two outcomes we could observe. And so those two things together are the sample space. Heads and tails together are the sample space, right? Now, suppose we do two coin flips, right? And so we're actually going to have two outcomes on the coin flip, right? The first coin flip and then the second coin flip. Well, what are the observable or potential outcomes that we could observe from two coin flips? Well, we might observe a heads on the first coin flip and a tails on the second coin flip. So we have heads, tails as the events that or elements that occur. Or we could observe a tails and then a heads, right? So that's this right here, tails, heads. We might observe two heads, right? Or we might observe tails and then another tails on the second coin flip. So the sample space for two coin flips is heads, tails, tails, heads, 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 tails, tails. These are the four potential outcomes we could observe from two coin flips. Then we can define an element or what the book calls an event. An element or an event is an object within the set of X, so I would have lowercase x and then I denoting that it's one sort of observation from this larger set of X, right? So this just reads that xi belongs to or is an element of X. So for example, if we have x equals 2, 4, 6, 8, right? An element 2 belongs to the set of X is represented by 2 belongs in the set of X, right? And so 2 is an element within X, 4 is an element within X, 6 is an element within X, and 8 is an element within X. That's an empty set. It's a set with no elements. We can skip that here. Okay, so let's go back up real quick and talk about maybe some political examples, right? So why would this be important? Well, imagine we're analyzing the 2016 presidential election, and just for the sake of clarity, it makes sense simple. There's two candidates, right? There's Hillary Clinton and Donald Trump, and instead of heads and tails, let's just say this is Hillary, this is Trump, right? So what is the sample space of vote outcomes of voting or election outcomes in this election? Well, either we're going to see Hillary win or we're going to see Trump win, right? So Hillary or Trump, that is the sample space. If we did and actually ran 2 elections, say we could run the election twice and the same candidates run, Hillary and Trump, right? Then the sample space for the coin or for these elections would be, you might see Hillary win the first election, Trump win the second election, Trump win the first election, Hillary win the second election, Hillary wins twice, or Trump wins twice, right? So that's sort of just giving some political examples up here. We might also say, if we're talking about party identification, what's the sample space of of the party that's going to win the election? Well, the sample space might be a Democrat wins the election, a Republican wins the election. If we had a Libertarian Party, a Green Party, right, we could add more sort of outcomes or potential outcomes to the sample space. Okay, so then we talk about the union of sets, right? And the union of 2 sets, A and B, is notated as A, U, B, right? A in the union of B, and that's the set containing all the elements that belong to set A alone, to set B alone, and to both set A and B, right? So that just gives you the notation there. And so this would be, say, the set of voters that are Republican and the set of voters that vote for, say, Hillary Clinton, right? What is that union of sets? Okay, so another example here, A, if A is 1, 2, 3, 4, and B is 5, 6, 7, 8, then the union of A and B would be 1, 2, 3, 4, 5, 6, 7, 8. So going back to the probably not a great example that I gave a minute ago, but what's the union of voters that voted for Hillary and say the union of voters that are Republican, right? That's going to be, a whole bunch of voters that all those voters plus all the other voters are. Let me give a better example. The union of voters that voted for Trump and the union of voters that voted for Hillary and the union of voters that voted for all other candidates in the 2016 presidential election. And then we'd have the entire set of all voters in the election, right? Those are some properties there. Okay, moving to the intersection, right? The intersection of 2 sets A and B is notated by this A with the sort of upside down U, B, right? And that's the set containing all and only the elements of both A and B, right? So that notation there, this upside down U, reads the intersection. And so we can read this as the set that contains all values labeled X, such that X is an element in the set of A and an element in the set of B. Going back to our same example, right? If A is the set of numbers 1, 2, 3, 4, and B is the set of numbers 2, 4, 6, 8, which numbers are in the intersection of A and B, it's only 2 and 4, right? That's what these sets have in common. So we might say, what is the intersection of Republican voters and the intersection of Hillary voters, voters for Clinton? Well, that would be only Republicans that voted for Hillary Clinton, right? Republicans that voted for some other candidate wouldn't be included in the intersection. Okay. Finally, we have disjoint sets, right? And so 2 sets A and B are disjoint, or they are mutually exclusive if A and B have no common outcomes, right? So if A and B have no common outcomes, then we say the sets A and B are disjoint or they're mutually exclusive. There's sort of, so an example would be the number, or so in an election such as the 2016 presidential election, each individual gets 1 vote, right? You're not allowed to go to the voting booth twice. So we could assume, as long as everybody's playing by the rules, that there's not going to be a set of Hillary Clinton voters and a set of Trump voters that actually vote for both candidates, right? That those sets are going to be mutually exclusive. You can't vote for Trump and then go vote for Hillary, and you can't vote for Hillary and then go vote for Trump. So the set of Trump voters and Hillary voters in the 2016 presidential election are mutually exclusive, assuming everyone's playing by the rules. So that's just a basic set of set theory. Where this stuff becomes important is in trying to understand probability theory, and we absolutely have to understand probability theory in order to do statistics.